Okay, as promised, we are back with the discussion on multi-step methods. We have been using single-step methods up to now, and now we are going to use multi-step methods. We will see that it can be used very nicely. In particular, there is an adaptive way to look at all those methods, and it gives very good answers. So that's what we will do. I hope you are able to see the slides. So let's continue. We begin our discussion with multi-step methods, and the methods that we have discussed up to now in this theme on ODEs, the ordinary differential equations. These are called one-step methods because the approximation for the mesh point Ti plus 1 involves information from only one of the previous mesh points, which is Ti. We are using only Ti and trying to compute the approximation for Ti plus 1. And although what happens is that function evaluation information at various points will be used, but we will not retain this information when we go for the next approximation. When you go to Ti plus 2, you would forget everything about Ti and you will concentrate only on Ti plus 1. That's what typically happens. So all this information used by these methods is obtained within the subinterval over which the solution is being approximated. The approximate solutions for all the previous ones is available. Whenever we are looking at Ti plus 1, you would have computed the solution at the approximate solution at T0, which is anyway the initial value. Then you would have computed the solution at T1, the solution at T2, and so on up to Ti. So all these are available to you. And then there is one more property, one more very important point to consider, which is that the error tends to increase with j because there is an accumulation of the error at various steps. So if you are looking at only Ti and compute Ti plus 1 from Ti, then the error tends to increase. Therefore, it seems reasonable to develop methods that use more accurate previous data when approximating the solution at Ti plus 1. You know, this is akin to something like trying to interpolate some points between Ti and Ti plus 1. If you have information only about these 2 points, then you will be forced to take only a linear interpolation, and then that is almost always not the correct interpolation. But if you have information on more data points, then you are going to get a better approximation. So that is what we keep in mind, and we go to the multi-step methods. So these are the methods which use approximation at more than one previous mesh points to determine the approximation at the next endpoints. And these are called naturally the multi-step methods. The precise definition is as follows. Suppose we have this initial value problem, y prime equal to f ty for a less equal t less equal b, and the initial value is given to be alpha. Then an m-step method for solving this initial problem is the difference method, which is given by this particular formula. It looks a bit complicated, which it should be because we are using data from many previous points. So you will be using not just the approximation wi, but also wi minus 1 up to wi plus 1 minus m. So it's an m-step method, right? So you will start from I minus 0, I minus 1 to I minus m minus 1. And therefore you will have wi, so 0 to m minus 1, that gives you m initial points, right? So we are taking a certain combination of these approximations of the previous m points previous to wi plus 1. And we also look at the function values. So we look at f of ti plus 1 wi plus 1 with a coefficient bm, f of ti wi, which is the previous one, with a coefficient bm minus 1, all the way up to f of ti plus 1 minus m wi plus 1 minus m. Okay, and then of course, you know, as one would expect, there is this step size h, which is multiplied to the function value. So this is our difference method. But what are the things in this difference method? There are these, it's for I going from m-1 to n-1, right? Because you cannot start from w0. You will have to have some first m values, and then once you have, so 0, 1, 2, all the way up to m-1, these are the first m values which should be given to you, and from them you will be able to compute the m plus 1th value, which is wm. So you will apply this to I equal to m-1, by which you will be able to compute the wm, and then the next values by taking the chunk of these previous m points. So I runs from not 0 to n-1, but from m-1 to capital N-1. Step size is taken to be the same step size, and it's the b minus a upon capital N. AI and bj, these are some constants. Most often these are real numbers, and you will have to have the initial values. So w0, which is anyway alpha, w1, which we call alpha 1, so on up to wm-1, which are alpha m-1. So this step, this is like instead of looking at the fixed point iteration method, if you look at the second method, instead of looking at the Newton-Raphson, if you look at the second method, then you need to start with 2 initial points. So this is similar to that. Once you are looking at multi-steps, we will have to have data on the first m nodes, and then we can begin to approximate the point value at the points which follow those first m points. Okay, this is what we will have to do. So how do you compute the m? But before we go to initial values, we notice that there is this particular very curious entry. Bm into f of t I plus 1 wi plus 1. We are writing a solution, we are writing an equation for wi plus 1, and there is already a wi plus 1 sitting here, and this is not a typo for a change, but it is indeed there. What may happen is that your bm may be 0, and if bm is 0, then you will have the equation, the difference method will have wi plus 1 purely in terms of the previous m points and the data associated to it. But if bm is non-zero, then you will have a complicated equation which involves wi plus 1 on the left hand side and a wi plus 1 in the right hand side also. So we will have to understand what to do with that. Okay, it looks that it is making things worse, but it will come handy later on. Okay, hang on, it's not going to be that bad. So this is what I said, that when bm is 0, the method is called explicit or open. That's because the difference equation then gives wi plus 1 explicitly in terms of the previously determined values. So bm is 0 would mean what? If this bm is 0, that means you have an equation for wi plus 1 only in terms of wi minus 1 dot 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 up to wi plus 1 minus m, and the function values and the corresponding ti and h. So wi plus 1 doesn't figure again in the right hand side if the bm is 0, and therefore this is called an explicit method. So this method will be explicit if bm is 0, but if bm is non-zero, then you have wi plus 1 on both sides, and this is then called an implicit method or a closed method, because then wi plus 1 occurs on both sides of the difference equation. So it is specified only implicitly. There is an equation for wi plus 1 that we will have to solve. That is slightly more difficult. Although the implicit methods, they are generally more accurate than the explicit methods, but to apply an implicit method directly, we will have to solve for that wi plus 1. Sometimes this may not even be possible. You may have several, your function value already might be some exponential value or something very complicated. And then your f t I plus 1 wi plus 1 will be very complicated. How would you be able to solve wi plus 1 equal to some other data plus an exponential again in wi plus 1? That would be very difficult to solve, but even if you are able to solve it, sometimes the solution may not give a unique value for wi plus 1. imagine that you have a degree 2 polynomial in wi plus 1, and so ultimately you will have a quadratic in wi plus 1, which by solving gives you two possible values for wi plus 1. So those are the problems with the implicit method. However, when we will use them, we will see that they give the accuracy of these methods is much better. Okay. So again, the starting values alpha 1 up to alpha m minus 1 will have to be specified. The initial value problem will tell you only the w of a, the w naught, which is y of a. That is alpha, only that is specified to you. So alpha 1 up to alpha m minus 1 will have to be computed. And so these are normally computed by starting with w naught equal to alpha, which is the initial value anyway. And then we generate the remaining values either by using a Runge-Kutta method or a Taylor method. Okay, so this is where the things we have learned up to now will be useful, that you either use a higher order Taylor method or Taylor method of order 1, which is the Euler method, or the most popular method, which is the Runge-Kutta method of order 4. We use that, and from this initial value we compute first m values. And once we have this, then we will be able to apply these explicit or implicit methods. So what methods are those? There are two main methods which are used quite often. The first one is an explicit method. So this is an explicit 4-step method. And this is by the mathematicians Adams and Bashforth. So they have devised this method, and this gives the wi plus 1 explicitly and 4 steps. So you will have wi minus 1, wi minus 2, and wi minus 3. You will need 4 points before I plus 1, and they are indeed these. So you will start with wi plus h by 24, 55 f of ti wi minus 59 f of ti minus 1 wi minus 1 plus 37 f of ti minus 2 wi minus 2 minus 9 f of ti minus 3 wi minus 3. How do we get all these numbers? These are obtained by, these are not, Adams and Bashforth did not just, go to sleep and they had a dream where they were given these values. What they did was that they did several other computations, and with respect to those computations, these methods were derived. But we will not go into those derivations. We will simply use these formulae. So this is an explicit 4-step method, and now there is an Adams-Moulton technique, which is an implicit 3-step method. So it's an implicit method. Therefore, when you are having wi plus 1, its value is given again in terms of wi plus 1, but it's a 3-step. So you will have I minus 1 and I minus 2. Only 3. It will not contain I minus 3. So we have wi plus h by 24, 9 f of ti plus 1 wi plus 1 plus 19 f of ti wi minus 5 f of ti minus 1 wi minus 1 plus 1 into f of ti minus 2 wi minus 2. So you see that this implicit method is looking very simple-minded. Here you had numbers like 55, 59, 37 and 9, whereas here the numbers are 9, 19, minus 5 and plus 1. And moreover, in these methods, all the ai are 0. You don't have wi plus a constant times wi minus 1 plus another constant times wi minus 2 plus another constant times wi minus 3. Those are not present. Only the corresponding function values are present. So these are the two reasons why these are more popular methods. And let's now try to see whether we can apply these methods. We have our favorite example now. So we have been playing with the initial value problem, y prime equal to y minus t square plus 1, 0 less equal t less equal 2, and y0 is 0.5 throughout this theme. Throughout our theme on ODEs, we are looking at this particular problem whenever we are looking for computations. Now, of course, we want to apply the previous methods. So we should compute some of the first approximations, and we will use the most popular method for doing that, which is the Runge-Kutta method of order 4. We start with h equal to 0.2. The distance is 2, H is 0.2, so you are going to have 10 plus 1, 11 nodes. So you will start with T0, T1, T2, T3, T4, T5, T6, T7, T8, T9, T10. T10 will be our 2. That's what we have. So H is 0.2. And of course, our W0 is 0.5. That's the initial value. W1, because we are using Runge-Kutta method, you can just apply that method of various KIs and so on and compute that W1 is this, W2 is this, and W3 is this particular value. Okay, so now we have W0, W1, W2, and W3. And we are going to use the 4-step explicit Adams-Bashforth method to compute the approximations for y 0.8, which would be W4. So W4 will use W0, W1, W2, W3. And having computed W4, we would want to compute W5, which is the approximation for y 1.0, y of T5. And for that y of T5, which is the W5, we will use W1, W2, W3, W4. Only the 4 previous values will be used. So the initial value given to us, that will not be used when we compute y of 1.0. Okay, so after computing these two values, we will also compare these with the Runge-Kutta method of order 4, because we could have continued with the Runge-Kutta method of order 4. You have computed from W0 up to W3. Why don't you just do W4, W5 and so on? That's also one thing that somebody may ask. So we will compare and see how we do, how we fare in comparison with the Runge-Kutta of order 4. Okay, so these are the formulas of explicit method, and therefore we have this formula, if you remember, 55 minus 59, 37 and minus 9, and then there is 0.2, which is the value of H. I will just write the final answer. It is 2.1272892. This is the value for W4. And now W1, W2, W3, W4 will give W5, which is 2.6410533. Okay, and now I have promised you that we will compare it with the Runge-Kutta method of order 4. So we have 5 columns. We have the actual y value, because I had told you the actual solution, the unique solution to the initial value problem. And so you can compute those values at 0.8 and 1.0. So those will be computed. The Runge-Kutta approximations will be computed. The error for Runge-Kutta, then Adams-Bashforth, and error for Adams-Bashforth. That's what we are going to do. So this is the column for the 0.8, and we seem to be doing slightly badly. The error for Runge-Kutta is 2.69 into 10 power minus 5, and the error for Adams-Bashforth is a bit bigger. 5.97, approximately twice the error. 5.97 into 10 power minus 5. What happens when we go to the next step? The next step is even bad, because this is 3.64 into 10 power minus 5, and this is like 19.4 into 10 power minus 5. So this is more than twice the error that we got for the Runge-Kutta method. So, okay, so although our methods are a bit complicated, we are not doing as well as the Runge-Kutta method is, but let's try to improve it. I promise that by the end of this lecture, we would have seen a nice way to improve the Adams-Bashforth so that we do even better than Runge and Kutta. Okay, so before we go to that, let me just tell you about the local truncation error. And this formalism of the local truncation error is not a surprise at all. Let's have the initial things out of the way. We have the standard initial value problem, which is y prime equal to f of ty. For t in the interval a comma b, y value at the initial point is alpha. And we have some difference method to solve, to approximate the unique solution to the initial value problem. So this is the multi-step method which we have been given, and we want to compute the local truncation error. And the local truncation error formula is tau of I plus 1 of h is equal to the simplest possible formula, which is that You call it yi plus 1, you call all the wi minus 1 and etc. to be yi minus 1. Remember that local truncation error does not take the accumulation of the errors into account. What it assumes is that the previous one was correct, and then it will say, given by the difference method, what would be the error. That is all that it would look at. So yi plus 1 is the correct value at the I plus 1 step, and yi are the correct values at the previous steps. And this highlighted part is the approximation for yi plus 1, assuming that all the previous ones are correct. So we just take the difference of them and divide by h. That is the error, okay, for us. So we observe that there is no h in this part. Therefore, when we subtract this by replacing wi by yi, we have divided by h, but for the function values there is an h which is sitting here outside, so we just cancel that h and put it with a negative sign. That's all we have done. So what we have done is, really, this is yi plus 1 minus wi plus 1 upon h, but the formula for wi plus 1 is assumed to be in terms of the previous correct values yi. This is the local truncation error. So once again, local truncation error assumes that all, now for the multi-step method, it will assume that all the previous values are correct, and then it will see what error there can be for the I plus 1 approximation. Okay, so this is the formula for the local truncation error. Now we are going to something called as the predictor-corrector method, which will help us improve upon that explicit Adams-Bashforth approximation, where we failed very badly compared to the Runge-Kutta method of order 4. No wonder that Runge-Kutta method of order 4 is so popular. So, okay, let's again, stress upon this, that implicit methods will give better results generally than the explicit method of the same order, but there is an inherent weakness which I have just now told you, that you have to first convert the method algebraically to an explicit representation of wi plus 1. So that is the thing that we will have to do, and this is not always possible. I have told you already, it might be something like x equal to some y plus 5e power x, and then you are expected to solve for x, and that would be very difficult to solve. So of course you can use Newton's method or second method, because whenever you want to solve for some particular value, you will put x on the other side, and then you have to look at the zero of the difference of those two. So we know how to find roots of the given equations. The equations can be any random equations, so we could use Newton's method or the second method or the regular falsy or whatever, but that will only complicate because it doesn't give the correct approximation. So you may do this, but it will further complicate the procedure considerably, because already you have an approximate wi, you have an approximate wi minus 1, so on up to w1. w0 might be correct, but up to w1 you have approximate values. You are going to get an equation for the approximate wi plus 1, and even for that equation you will only solve some approximate value. So the approximation is taken too far, and we would not want to do that. So what we are going to do is not what one would expect us to do. So in practice, implicit multi-step method are not used as described above. They're not simply going to be used to compute wi plus 1. What they are going to be used for are the ways to improve the existing solutions. So what we are going to do is that this is a certain combination. So you first have an explicit method to compute wi plus 1, okay, and then you put that wi plus 1 on the right hand side of an implicit method. That will give some formula for the left hand side wi plus 1. That implicit method improves the prediction, and this is called a predictor-corrector method. So what we are going to do is that we have two formulae. We have an explicit formula for wi plus 1 in terms of wi and lower. So you get one value of wi plus 1 from that. You give it a different name, say zi plus 1. and you use zi plus 1, zi which are equal to wi and so on in the implicit formula. Now implicit formula is a equation for wi plus 1 in terms of wi plus 1, wi blah blah blah. So there you use the earlier computed value of wi plus 1 in the right hand side and solve that, compute that again for wi plus 1 which is there in the left hand side, thus improving the approximation wi plus 1. Let me give you an example to make it clear. Suppose we have a fourth order method for solving an initial value problem. The first step would be to compute w0, w1, w2, w3. We know how to compute that. We will use either the Taylor method or a Runge-Kutta of order 4. Okay, so this is done. We put it aside, we compute the values, keep them on some shelf, and we will take them when we need them. Okay, so now there is this explicit Adams-Bashforth method. What does it do? It will tell you how to compute W4 using these 4 initial values. So we use the Runge-Kutta of order 4 to compute W0 up to W3. Then we compute an approximation which we call W4P. We don't call it W4, we call it W4P, P for prediction. So this W4P, this is an approximation of YT4, and for that we use this explicit Adams-Bashforth method. Okay. So using the explicit Adams-Bashforth method, we compute W4P. This is the formula for W4P. Okay. Having computed this approximation is then improved by inserting this predicted value of W4 in the right hand side of the 3-step implicit Adams-Moulton method. You remember that the 3-step method for Adams-Moulton will have W4 equal to W3 plus H by 24, and then you will have something f of T4 W4. So we put there T4, and instead of W4 we will put W4P. This is what we do. So you have W4 here, we put W3, W2, W1 as they are, but when we come to W4, we use the value which is predicted by the explicit Adams-Bashforth. So the explicit Adams-Bashforth, so the order will be, you use the Runge-Kutta to obtain first few initial values, then use Adams-Bashforth to predict a value, and then use that in the implicit Adams-Moulton method to improve upon the W4. This is what we are going to do. Okay, the only new function computation which is required is this, because all the previous one, f of T3 W3 to T2 W2 and T1 W1, they have already been computed. So just one more function evaluation is required in the corrector equation. All of the others have been already computed. And this is the value W4, which we use to as the approximation of YT4. So you remember we had kept some values in the shelf, which were W0, W1, W2, W3. You put this in the next part of the shelf, next stack, or whatever you call it, the next corner, W4. So now we have W0, W1, W3, W4. So use the 4, 1, 2, 3, 4 to compute W5, again using the explicit Adams-Bashforth, W5P, the predicted one, and put that again in the implicit Adams-Moulton method to get the W5. Put that in the shelf. And now using 2, 3, 4, 5, you compute the predicted 6th. Put that in the implicit formula, get the 6th value, put it in the shelf, and this is the way we continue. So the technique of using the Adams-Bashforth as the predictor and Adams-Moulton as a corrector is repeated to find W5P and W5 and so on up to you get the approximation to the last point, YT_N, which is YB. This is the predictor-corrector method that we use. And you might think that once we have obtained some value for YTI plus 1, which is WI plus 1, why don't we again put it in the implicit equation and repeat the process there itself? That is one thing that you might think but that is not so effective. So if you really want to improve upon the approximation, it is better to use the implicit formula rather than the solution. So this, if you keep repeating the Adams-Moulton, trying to improve the approximation wi plus 1, it is not going to give you y of ti plus 1, because really speaking y ti plus 1 is slightly away, and the difference equation has something to do only with the previous values and the I plus 1. So within themselves, the point basically is that you have all our approximations, and using only the approximations, there is no way that you are going to reach the exact value. So these approximations, even if you keep repeating, it will perhaps converge to a limit, but it will converge to a limit which corresponds to only the difference method. It will not go to the y t I plus 1. So if you rather want to get a better thing, you should try to use reduction in the step size, which will typically give the better solutions. Okay. And let's now again complete this lecture with an example. We have our standard example, and we use the Adams fourth order predictor-corrector method. H is 0.2 and starting values from the Runge-Kutta of order 4 to our standard initial value problem, the same problem that we have been dealing with all this while. And the initial values, which we have already computed, W0, W1, W2 and W3. Now we want to compute the fourth predicted value. That is this 2.1272892. You know this because this we had already computed a few slides back. Okay. Using this value, we now want to get an improved approximation to y 0.8. Okay. So that is given by this formula, because we have to put it in the Adams-Moulton method, and we have indeed put it here in the Adams-Moulton method, and the answer would then be 2.1272056. Okay, and the predicted and corrected value for the next one, which is W5P and W5, they are again computed in the same way, and these are the values. Okay, so how far have you done? So we now need to see whether we have improved slightly, because if you were using only Adams-Bashforth, then we failed miserably compared to the Runge-Kutta method. But have we done better now? So you will see that the values computed using the this is something that we had done earlier, that our earlier application of Adams-Bashforth gave us inferior values. The errors were bigger than the errors for the Runge-Kutta. However, now we have managed to do better. So although we may have started badly with the Adams-Bashforth, but now by combining with Adams-Moulton, we have managed to end this lecture on a brighter point. And let's see how the errors behave. This is the y 0.8. This is the Runge-Kutta approximation, this was the error, 2.69 into 10 power minus 5. Now it is only 2.39 into 10 power minus 5. It has reduced slightly, but it has reduced. And even for the next one, whereas this 3.64 was the into 10 power minus 5, this is the error for the Runge-Kutta. And if you remember, for Adams-Bashforth, it was something into 10 power minus 4. We had gone to the next decimal point in the error, whereas here again the error has reduced. So this, the combination of explicit Adams-Bashforth to get the predicted value, and then using it in the implicit Adams-Moulton method to correct or to improve upon the value has worked well. We give the table of the remaining values in the following slide, and you see already that when you are using this predictor-corrector method, then we are doing quite well. For instance, if we were using the 0, 0, the first row is of course because the initial value is given to you. The second row, third row and fourth row. So the values for 0.2, 0.4 and 0.6. These are obtained by using Runge-Kutta of order 4. Okay, what are the errors? We have So 53, let me just, ignore the points and decimal things and so on. We will just count it as real integers. So the error at 0.3 was 53. The error at 0.3 became 114, which is double than this. But if you want to really think, we added 60 to 53, okay, to get 114. And the next error is 186. So you had to add 70 to get the error at the next step. And therefore, if you were using only Rungakutta of order 4, the next error would have been added as 80 or 90 or maybe 100 and even more. Whereas we have gone from 186 to 239. This is where 0.38, this is where we have now been able to use the predictor-corrector method. So instead of getting the higher error, we have managed to reduce the error. Okay, and even the next error is not as bad as 114 to 186. 239, which is roughly like 240 to 305. So this error from 0.8 to 1 is less than the error going from 0.4 to 0.6. Okay, and then of course then the errors increase, but in the end we see that if you ignore this 1.10 is, definitely for first 3 decimal points you have the correct answer, and if you were just going to stop before 2.0, you would have had correct answer for even up to first 4 decimal points, for first 4 decimal digits. 4 digits after the decimal point. So the errors are definitely better. If you were to take x even smaller than 0.2, then the errors would definitely be much better. So this is what we have for the current discussion on multi-step methods. I am aware that this lecture is also gone slightly beyond half an hour, so I will not say anything more and stop this and see you in the next lecture. Thank you. Bye.